Thank you very much for the introduction, and thank you very much to the organizers for organizing this workshop and giving me the opportunity to present here this overview, or what is supposed to be an overview, at least for both experimentalists and theoreticians, I hope, on all the different techniques that by now have been developed to measure thermal transport. Of course, we've seen several techniques already coming by. Yesterday we had some fantastic talks from theoreticians where some experimental techniques were already described, and today in the morning, of course, also some experimental talks, but I hope that this can still serve as a nice overview of all the different things that are out there, and some novel developments that are taking place at the moment. Okay, so I want to start from the basis, which is thermal conductivity, right? We want to measure thermal transport, and generally then we talk about the thermal conductivity. So the thermal conductivity in its easiest way is described by Fourier's law, no? Where we see that there is a linear dependence between the temperature gradient and the heat flow, and that linear dependence is the thermal conductivity. So in very simple terms, what we need to measure the thermal conductivity is we need a very small thermometer, no, so that we can measure the temperature at the nanoscale, and we need a way to get the heat to truly flow through the nanosystem and not just flow through its environment or flow through the substrate or anything like that. What I mean with that, and why that is a special requirement, which, for example, if you look at electronic transport, is not really looked into, I like to show through this graph. So what we see here is just a whole bunch of materials, and on the vertical axis we have the thermal conductivity, whereas on the horizontal axis we have the electrical resistivity. So what we see when we look at the horizontal axis is that we have 28 orders of magnitude of electrical resistivity to play around with now. So it's very easy to find a material that is less electrically conductive than the system we are interested in. We can put it on top of that material, and we can safely say that all the transport, the electrical transport through our substrate, will be negligible. But instead, if we look at the horizontal axis for the thermal conductivity, the range is less than 5 orders of magnitude. So while for bulk system this is not an issue, once we go to nanosystems where the dimensions of your system becomes easily 6 orders of magnitude smaller, this becomes a problem. You cannot just ignore what is going on in the substrate anymore. So you need to use special techniques to eliminate the effect from the substrate. And because of this, because of these special requirements that thermal conductivity measurements at the nanoscale have, there has been a wide range of techniques that are being used right now, that have been developed over time in the past 10-20 years, when the research into thermal transport at the nanoscale sort of started booming. But in very simple terms, we can divide it into 2 classes, which are either electronic measurements, of which I showed 2 examples here. This is a Triomeca system that we saw already before in a talk, and this is a suspended bridge system, which you could have seen on some posters. And the other class of measurement techniques are optical. So what we see here is a Raman measurements. Now we see the Raman shift as a function of position, and then you have a wide class of pump probe techniques, being either the photoacoustic effect, time domain thermal reflectance, or any several other techniques actually. For the moment, these pump probe techniques work very well for arrays, thin films, and nanostructure. Bulk, but not so much yet for single nanostructures. But since they have their own advantages, I would like to describe them in more detail as well. So I will start with electronic measurements. The basic elements that you need to do electronic measurement is a lock-in amplifier, and then a probe station or a wire bonding, so that you can get an electrical contact to your system. These kind of measurements are relatively straightforward to set up. They are the closest thing to what Ricardo probably would call the pressing the button to get your data out kind of measurements, except this one doesn't have a button, but the idea is the same. So they are very easy measurements to set up. Now, again, because we already have a lot of understanding of this measurement of the electronic transport, and we can use all the knowledge from the electronic transports to measure the thermal properties here. And the most common way to do that is the Triomeca method, which you can do in several ways. But the easiest way is the self-heating. So you just send a current, an oscillating current through the system that you want to measure. And because of this oscillating current and the thermal anchoring at the ends, you get this parabolic heat profile that is building up. So what you need to do this kind of measurement, first of all, is of course a conductive sample. You want to send an electrical current through it. And then you can send an electrical current through it with a certain frequency. No? And then the smart thing why it's called the Triomeca method is that the dissipated power now is proportional to the square of the current. No? So if we square this current, now we get a term that has twice the frequency, which in part is also proportional to the change in temperature. Then this incoming power has to be equal to the outgoing power. But if we are assuming that these fluctuations are slow, we can only look at the second part of this term, where then we get sort of the steady state to omega method, where our change in temperature is simply proportional to our current squared and to with a frequency of twice the frequency that we were sending in. So this is, again, just to reiterate, this is for very low frequencies. No, so then if we measure the voltage, we have to, again, we measure the voltage with the same current. So we multiply again with our oscillating current signal, which adds, so now it's proportional to the current to the third. And we also see that we are proportional to the third frequency. So that's why it's called the Triomeca method, and that allows us to extract separately, let's say, the signal that is coming from the not heating up to the signal that is coming from the heating up, right? So what we need for this is once we measure the voltage, we see that it's proportional to the current, our resistance at the beginning, which we can extract from our 1 omega signal, and the proportionality of the resistance to temperature. You know? So how does our specific sample, how does the resistance, the electrical resistance of our sample change due to a change in temperature? So far I assumed steady state. So I said the frequency is very small compared to the typical thermal time constants of the system, the thermal dissipation. So what we get then is essentially that's our thermal profile is exactly following our oscillating current. No? So we see that when our current is maximum, our thermal profile will be maximum as well. And when there's no current, it will reach minimum. So our temperature profile is also continuously fluctuating along with the same frequency. However, once we start increasing the frequency, we start seeing the effect that the heating up is not, it doesn't reach steady state anymore because of this, because the heating power is changing faster and that the system reaches steady state. So we see now that the fluctuations start getting less and less. And then in the ultimate limits, what we see is that it's not fluctuating along with our current anymore, but we still see a signal. And now our signal is actually proportional to the specific heat and not proportional to the thermal conductance anymore. So this is a nice extra bonus thing with this time dependence that you get out of it, that you can not just extract the thermal conductivity, but you can also extract the specific heat of the system. Now, of course, in this whole explanation, I made certain assumptions, which I think are important to be aware of to try to understand what kind of data can we extract from these kind of measurements and what might be a little bit more tricky. So the first assumption is that our fluctuations in power due to the temperature fluctuations are small. No, I considered, sorry, if we go back here, I considered here that that the power which we're heating is proportional to R0. No, so we need the dRdt to be relatively small for that assumption to hold, whereas you want it to be relatively big, of course, to have enough signal coming out. So that is a little bit of a tricky, let's say, system choice that you have to make when you want to do these kind of measurements. The second assumption that we made was that the losses to the environment are small or negligible in the thermal sense, at least, which is overcomable. There are more advanced models where you are taking into account the losses to the environment, but as already pointed out also in the morning, the more complex you make your model, the more input parameters you're getting, and the easier it will be to make mistakes and to get an increase of errors because of the many fitting parameters that you're getting. So ideally, you're trying to avoid these losses to the environment. And the final assumption that we were making is that the resistance change is only coming from the sample itself, right? We are interested in how much is the sample itself changing in temperature, but if we use connecting lines to contact these samples, the connecting lines will also heat up due to this Joule heating, and we don't want to see that signal ideally. And one way to avoid that is to do a 4-point measurement. And the idea of a 4-point measurement is that one arm is used to send the current and the other arm is used to measure the voltage. And if we assume a perfect voltage meter, then no current would be flowing through this voltage meter. And as such, in these arms, there would be no potential drop, and we could truly be measuring the potential drop over our system. So now imagine that after this very short introduction, you got inspired to start doing your own Triomeca method. Now, what do you need? I already mentioned for the general electronic measurements, you need a lock-in amplifier, you need a probe station, you need to make contact somehow. But now for doing your own Triomeca methods, you will need to work on a conductive sample, an electrically conductive sample. Ideally, you want to make your sample floating, and you want to create, through some nanofabrication, you want to create 4 contacts to the sample. And then you want to use a lock-in amplifier to measure the voltage change at the third harmonic. Then you pump it down. The first thing that you need to do is calibrate this resistance change as a function of temperature by changing the baud temperature. And then if you want, you can change the frequency as well to extract both the thermal conductivity and the specific heat. So you end up with a system like this, which is still relatively easy to make processing wise, and it's relatively easy to measure, but of course there are limitations in what kind of systems you can measure with this. So then if we look at a typical data set that you would be getting out from here, like I said before, the Triomeca signal is proportional to the current to the third, now linearly proportional. So you would be ramping your current to get more data points out, and then checking your Triomeca voltage. And then from the proportionality between the two, and from already having pre-calibrated your change in resistance, you can extract the thermal conductance. And the second thing, like I said before, you can also change the frequency. And then what you will see is in the low frequency regime, in the so-called linear regime, you can use the approximation that I said before, where it's quasi-steady state. So you can use it to extract the thermal conductivity. And then once you go to very high frequency, you see that your in-phase signal drops. No? So your signal is not able to follow anymore your heating power, and instead it will phase shift with respect to your heating power, and that then will be proportional to your specific heat or your thermal diffusivity. And the interesting there, which will come back later with the ultra-fast techniques, is that the thermal penetration depth is proportional or is inversely proportional to the square root of the frequency, because the faster your frequency is oscillating, the further the slower your frequency is oscillating, the further the heat has time to travel before already the boundary conditions on top are changing. So you can use this in a way to control, if you're using this to measure thin films, to control how deep into your thin films are you measuring, which is, I think, a nice bonus for this method. So Triomeca method, when should you use it and when shouldn't you? The advantages are very easy processing and very easy measurements. No, the pressing a button to get your data out kind of measurements. And the advantage is that you can dynamically change the distance over which you are measuring now by changing penetration depth, and you can extract the thermal conductivity and the specific heat. The disadvantage is you are quite limited in what kind of samples you can measure with this, because they need to be electrically conductive. You also don't have a full control over the heat flow, because you always have that the maximum temperature will be in the center and the heat will always flow from the center outwards. So if you have, for example, inhomogeneous samples, or you're looking for asymmetric effects such as rectification, then this is probably not the method for you. And along those lines, the signal is averaged over the entire sample. So again, if you have inhomogeneous samples, it can be very difficult to properly model what is going on at each different part of your system. So the typical usage of this right now, where I see it being used, is heating of metal strips. These metal strips can then be used to monitor how much is the layer underneath warming up, but for that also we've seen some other techniques which will come by later. Or at least what you would like is homogeneously conductive samples. One side place where you see the Triomeca method still applied a little bit more is for scanning thermal microscopy. So the idea there is that you put either the Triomeca, so you put a resistive heater on an AFM or STM tip, or you use the thermal voltage, so the CBEC, to measure on an STM tip very locally what is the temperature here. So then the advantage there is that this tip provides a very good spatial resolution down to a few nanometers, and you can have a very good control over where you're measuring and what you're measuring. So it's very useful for doing local measurements. So for example, in the previous talk, we saw these arrays, and you really want to make sure that your heat is going through the nanowire and not through the structure around it. No, then you can use an scanning thermal microscopy tip to really make sure that the heat is going where you want it to go. So you can use this in two ways. You can either put a heater on the tip and use it to create a heat flow from the tip into your system, or you can use it in thermometry. And it can be operated either in air or in vacuum. But the problem with this scanning thermal microscopy is because you have this very small tip, the sample to tip thermal resistance is very hard to monitor. So when you want to know the entire thermal resistance of your system, you always have the series resistance of the tip to your sample in contact, and that makes a quantitative analysis hard, especially when you use it as a heater versus when you use it as a thermometer. But yeah, a typical measurement system would look something like this, where you have this AFM tip, where you have either through high doping, or it can be metallic, you have these very conductive legs, and then you have a less conductive area in the middle, where then the majority of your resistance is coming from in case you want to measure the temperature, or also where the majority of heat is being dissipated in case you want to use it as a heater. There are two ways that this technique right now, as far as I know, is being used, which is either for near field heat transport. Of course, with AFM tips and STM tips, you don't just have in the horizontal plane a very good spatial resolution, but also in the distance between your sample and your tip, you have a very good spatial resolution. So what you can do then is to create an STHM tip and slowly get closer to a sample, no? Which in this case, you're not even interested in what is going on in this sample, but you're interested in what is going on in the gap between your tip and the sample. So generally these studies are done in ultra high vacuum, because what you get when you put these kind of tips close in air is that it starts forming bubbles. So the conduction would be convective in nature, and what they're looking for is radiative transfer. Yeah, so you would change the distance from a hot surface to determine the heat flow. And I think an interesting result, as you can see here, is that you can see here the blue graph represents the heat flow as a function of distance, whereas the red graph represents the current flow. So we see that the heat flow is already setting on at a larger distance than the current flow. So before you even get any tunneling effects, which might be a concern for these kind of systems, you can already use it to greatly enhance the heating just because of near field radiative effects. The other way that STHM is being used is to locally measure the temperature on samples that are being heated up through other means. Generally, these other means are then the self-heating method. And the nice thing then is that because of, again, this frequency dependence, you can extract or you can eliminate the thermal boundary resistance between the tip and the sample by comparing what is going on at the DC level and at a higher frequency level, no, at the Triomeca level, because the DC level is also influenced by this thermal boundary resistance, whereas the Triomeca signal is only coming from the heating up of the tip itself. So now by adding this addition, no, on top of the general self-heating method, now we also have the spatial information. But of course, we are getting away from our very simple measurement system where we just press a button and we get our signal out, and it becomes already a much more challenging system. So this is typically used for conductive samples where you do want this kind of spatial information. Yeah, so maybe one thing, of course, the signals now are dependent still on how close you are getting with your tip. No? So there needs to be a heat flow from your sample into your tip to be able to measure anything, for your tip to warm up and to be able to measure a temperature there. But that also means that your tip is influencing your system. So there's always a trade-off between this. So ideally you have a very good signal to noise ratio to be able to stay far away to reduce the influence from your tip on your system while still getting a good temperature measurement out. So maybe a very technical detail, but for that, for all the electronic measurements these days that people are doing, they generally use a Wheatstone bridge, which is just a way, because normally you measure the change of resistance. So you have a very large absolute resistance, which can be kilo ohms. And on top of that, you want to measure a change of a few ohms, which can be technically challenging. And the Wheatstone bridge is a trick basically by using this set of resistances where if the Wheatstone bridge is balanced, or as you can imagine, if this is perfectly symmetric, all the resistances are the same, then there is no voltage between these two legs. But when you then start changing one of the resistance, you will start building up a voltage difference between these two legs. And as such, you can measure the resistance change directly rather than measuring the absolute resistance and doing a differential measurement like that. So this is these days also a crucial element in all the electronic measurements. The second electronic measurements that I wanted to talk about is avoiding the problem of needing to have a conductive sample by using conductive heaters and thermometers separately, but at the cost of a more difficult processing, and that is the suspended bridge method. So now what this consists of, if we, it's more visible here than on my screen. What you see here is two very long suspended membranes, because again, we need to make sure that our heat is truly is not flowing through any substrates. That's why we need to suspend them. Then we put a nanowire in between, and on top we have a metallic meander that we can then use to heat. So we can heat up one side, and we can also use the change of resistance on the other side to measure the temperature. So now we don't need an electrically conductive sample anymore, because our metal is taking that place, but at the cost of having to create these rather difficult platforms. Yeah. So the processing of this sample is rather difficult, but I think in view of time, I will skip over it. If anybody wants to start these kind of measurements, I'm happy to talk you through it. Rather, what I would like to talk about is the kind of assumptions that we're making here to analyze these problems and what kind of problems that is introducing. So to analyze this, of course, we cannot just directly take the wire properties, because what we have here is a thermal divider. Some of the heat will flow still away to the environment through the suspending beams, whereas a part will flow through the wire and then away to the environment to the suspending beams. So we have two equations from our two different thermal balances, and with that we can extract all of our parameters. but we need to make two assumptions. And there are two possible assumptions that people are making for this, which is either our two beams are conducting in the same way, or our sample is symmetric. No, so even though this system gives us the best control over, or a better control over heat flow, we can now change the direction of our heat flow. There's still this difficulty when you want to measure rectifying behavior, for example, because because you need to make a certain assumption. So now when you want to measure rectification, especially, you need to first take a symmetric sample to identify how asymmetric are my devices. And then after that, you can use that determination of the asymmetry of your devices to determine the asymmetry of your actual wire. But the second assumption that we were also making along the fly is that the temperature of the wire, the temperature gradient along the wire, is equal to the temperature difference between the hot platform and the cold platform. So there are two reasons why that might not be true. First of all, if there's a gradient along our platform, then that's obviously also not true anymore, because we are measuring at a different spot than where our wire is. But luckily, from the fact that these are suspended over such a long distance, that doesn't seem to be so much of a problem. But a much bigger problem for these kind of measurements is the thermal contact resistance. As an example, one of the measurements I did was on nanowires of different diameters. And as explained before, what you expect is that the thinner you make your nanowires, the lower your thermal conductivity becomes. As you can see, this model, this red line, did not fit my experimental data points in blue at all. No, instead, what we found was that the bigger we made the diameter, the smaller the thermal conductivity became. And we managed to explain this because while the wire conductance is scaling quadratically with the diameter, the contact resistance is scaling linearly with the diameter. So the larger we make our wires, the larger we make our system, the more important relatively the contact resistance becomes. No? So here that's drawn maybe a bit more clearly. The blue line is giving you the contact resistance. The green line is giving you the wire resistance. So then the total is the red line. So you can see for large diameters, you are completely dominated by the thermal contact resistance, and you're not actually measuring the wire properties anymore. So that means that this method can ideally be used for very poorly conductive samples, where you can make the claim that where you can first of all make the claim that your wire resistance is much more than your contact resistance, and secondly, where you also get the benefit from the very good thermal resolution that this method gives, which can go down to even below millikelvin temperature resolutions. I want to talk about a few ways that people have worked to avoid this. One way was to, just like we did before with the electrical measurements, to make a kind of thermal 4-point measurement. No, so instead of 2 thermometers, we now use 4 thermometers. Now 2 thermometers are then used, or one of them is used to heat, and the other 3 are used to check how much is the heat flowing along different lengths. No? Now, of course, we cannot make the assumption that we could do in the electronic system that there is no heat flowing through our thermometers anymore, because these thermometers are metal lines that are essentially the same as the heaters. So the model gets a little bit more complicated than in electronic 4-point measurement, but in principle, this can help you to extract the contact resistances and thus get the true wire resistance out. But with one single measurement, whereas before we needed to change either the diameter or the length, and then do the scaling with diameter or length to find the contact resistance. Again, this is assuming that the sample is non-rectifying. So again, this method cannot be used when you have any inhomogeneities in your sample. So it's again just for homogeneous samples. And of course, you need it to be relatively long to be able to bridge all these thermometers. So that brings me to the advantages and disadvantages of the thermal bridge method. The advantage is that because of using external heaters and thermometers, you can use it for any sample. In principle, you have full control over the heat flow direction. Again, in principle, And you have very accurate temperature measurements down to millikelvin or even below. So you can also work with very small gradients where you don't have the problem that the temperature dependence of the thermal conductivity starts playing a role. However, contact resistance remains a problem, which means that it can essentially only be used for very poorly conductive samples. You have no spatial information on what is going on. So if you have inhomogeneous samples, you can measure them using this, but still you will get the overall effect of the system, whereas you might be interested in what is taking place in each part of my inhomogeneous sample. And the processing is probably among the most difficult for any of the techniques I am describing here. So the typical usage, like I said already several times, is samples with a very low thermal conductance, samples with an expected rectifying behavior. Like I said, it requires some more work, but at least you have this control to flip around the heat flow direction. So that is the scale where you would apply these. Now I wanted to also measure a few thermometry methods that are not very common within this community, but are more being used within other communities, that being either the quantum noise community or the quantum information community or the biophysics community, where they also are interested in measuring temperature at a very small scale without actually introducing heat flow. Just so that also the experimentalists are aware of the full scale of possibilities that are there and maybe can extend their options even more. So one of those things that is used for quantum noise thermometry is SQUID, a superconducting quantum interference device, where I'm not going to go into too many details, but essentially you have a superconductor here, and you have two legs. And here at the outside, the current is depending on the interference between the currents from these two legs. No? So you can change the effective path length through one of the legs by changing the temperature. And then in that way, you can use this to measure the temperature very locally. Generally, this is then put on a tip to very locally measure the noise in a system. Of course, this only works at cryogenic temperatures, which is probably why within this community we don't see it very often. But if anyone is interested, I thought I would just quickly mention that this technique is also out there, because it does give a very high temperature sensitivity and a very high spatial resolution. So now I am finished with the electronic parts of the measurements, and I would like to go to the optical measurements. So again, for the optical measurements, we have a few key components that you will see in any optical setup, which are a laser, an objective, and a spectrometer. But then probably you want some mirrors to get your laser lights to go where you want it to be. You want a few filters here and there. Possibly you want to modulate your laser signal. So soon your setup will look slightly more complicated than what we saw before, which is of course a disadvantage of the optical measurements, but I will also go over the advantages. So whereas before the pushing a button technique might have worked still and things can be automatized and done relatively fast, these measurements in general will take a little bit longer to set up and to perform. So for the optical techniques, there are three things that are being used, but I will focus on two things that are being used for single nanostructures, I should say, because in the end I will also talk about the ultra fast techniques that we've seen coming by, which are obviously also optical techniques. But for the single nanostructures, essentially you can look at fluorescence, but that is not being used that much. The idea there is that you have a fluorescent particle on a tip and locally measure the change of fluorescent properties, which are dependent on temperature. But the more commonly used are to use luminescence or to use Raman. So the first one that you could use or that you could think of using is micro-PL, because several luminescent properties depend on temperature. Now you have the wavelength, you have the line width, and you have the intensity that will generally depend on temperature. But on top of that, you have also the lifetime of your optical decay. So by monitoring any of these temperature dependent properties, and by knowing the calibration of these properties to temperature, you can measure the temperature. So typical usage is very similar actually to what we've seen in the first talk this morning, where you put a sample over an etched hole so that it's thermally isolated from the environment. You shine with a laser onto your sample. You make a certain assumptions again to model the heat flow into this kind of sample, which are that your contacts are perfect, as explained before, and that your holes are nicely circular. And then by measuring the temperature locally, by knowing how much of the power is absorbed, so how much is your heat flow, you can extract the thermal conductivity of this system. But this measurement technique is actually not that common for reasons I will go to later. The more common way to use a micro-PL is by embedding it into a tip. So the way that you would do it there is you have a diamond tip where you have an NV center. So an NV center works like an artificial atom within this diamond tip. No? So again, this will be a luminescent system, but on a very small scale. So you can use it to measure temperature at a very small scale. And because diamond is biocompatible, this is very much used in biophysics to check how the luminescent properties of this system are changing. But a big way that I think this community is more familiar with, so that I would like to go to now, is Raman spectroscopy. The idea behind Raman spectroscopy versus luminescence is that for luminescence you need the sample to be luminescent, which is a more stricter requirement than for a sample to be Raman active, which is more often taking place. So we've seen several talks already about Raman spectroscopy, but the idea is that we send a laser onto our system now, and then depending on where our electron is within our vibrational energy states, it will be excited and then it will fall back. And in this case, it will actually excite a vibration or excite a phonon. So the outcoming light will have a slightly lower energy, and that is called Stokes scattering, or in the case of anti-Stokes scattering, instead we see that we absorb a phonon, so that the photon gains a little bit of energy, and in that way we measure the energy of the phonons. So I think already, so a typical spectrum then would look like this. Of course, still most of the light will scatter without interacting with any vibrational states. That is called Rayleigh scattering. No, the reason why the sky is blue is often said. But there are some cases where you would see that it does interact with a vibrational state, either by gaining a little bit of energy, in the anti-Stokes side, or by losing a little bit of energy on the Stokes side. And because in this way we are measuring the phonon properties, this gives us a lot of advantages, I think, for measuring the thermal transport, because they are of course also often dependent, especially if you look at the phonon part and not the electronic part, they are dependent on the phonon properties. So by using Raman spectroscopy, we can check these phonon properties on the fly while checking the temperature. So also for Raman thermometry, we have 3 things that can generally be checked to check the temperature, which is either the peak position or the line width, which is coming from enharmonic effects. Now they are coupled through the Kramers-Kronig relation. So here you see a typical example. The black circles represent the peak position as a function of temperature, whereas the red circles represent the full width half max. As you can see, the full width half max is a little bit more noisy. It depends. The signal to noise ratio is a little bit harder to extract than for the peak position in general. So the peak position is generally the more common way to measure temperature using Raman. And maybe one thing that is important to point out here, which might not be immediately obvious, is because with this way of using Raman thermometry, we are checking the enharmonicity. So we are checking how our phonon modes that we just created or destroyed, but in this case created, decays to all the other phonon modes. So even if the system is very much out of equilibrium, we have certain phonon modes that got excited more than the other phonon modes, because this is looking at the enharmonicity. We are effectively measuring the average over all phonon modes. We are measuring the average of the entire system. One disadvantage of this is that it only works from a certain temperature. So here you see some data for silicon, and we can see only from 100K, let's say, the peak position starts dropping, and before that the curve is rather flat, so it cannot be used effectively for thermometry. The reason why I'm pointing this out, that I'm measuring the average with the peak position, is because the other way to measure the temperature using Raman scattering is to use the ratio between Stokes and anti-Stokes scattering. So as I explained before, with Stokes scattering we are creating a phonon. No? So we don't need another phonon to get a Stokes signal out. So it's independent of the amount of phonons, whereas for anti-Stokes we are absorbing a phonon. So that is directly proportional to the number of phonon modes that are available for that specific transition. No? So as you can see, since the number of phonon modes available depends on temperature, through the Bose-Einstein statistics, but because this is mainly used at higher temperatures, generally the Maxwell-Boltzmann statistics are used. But from the ratio between these two, we can extract the population of a specific phonon mode, and as such that can be translated to a temperature of that specific phonon mode. So unlike with the peak position, where we are truly measuring an average over all phonon modes, the Stokes anti-Stokes gives us specific information about a very specific phonon mode. So here in this plot is just drawn what I said before, where you can see that the ratio of intensity will depend on temperature, but of course it's also dependent on at which energy your peak is. So for gallium arsenide, where the phonon modes have relatively low energy, you will see a much steeper increase of your change in ratio than for something like graphene, where the phonon modes are much higher energy, and as such, thermally exciting these phonon modes takes a much higher temperature. No idea what's going on here. Okay, sorry. And so then we know now that we can use Raman to measure the temperature, but how is that applied in Raman thermometry? We've seen this already before this morning in a talk, but I want to go over it in maybe a bit more detail. So in this model, what I'm assuming is we know how much power is absorbed from a laser. We can move our laser between our two contacts, where also we know, or we can model or fit our contact resistance, which is given by RL or R respectively. And then we see just that it works as a heat flow divider again. No? So depending on the wire resistance or the total thermal resistance from our laser spots to the left and to the right, our absorbed power will divide itself in a left flowing heat flow and a right flowing heat flow. And that will result in this kind of quadratic dependence. But as already pointed out also before, to get truly the thermal conductivity out, we see that our change in temperature is proportional to absorbed power, right? So we need to know how much power is absorbed. Now in bigger systems, in bulk systems, or even in some thin film systems, what you can do for this is simply put a power meter underneath and check how much your power has reduced when you put your system in between, and use the difference between these two. But for nano systems, often this is getting a very small difference, and as such, the error can get very large. So what is also commonly used for these kind of systems is to actually use optical simulations to check how much of the power is absorbed. But the problem with the optical simulations is that it depends on the diameter. So here I show some simulations for different diameters of silicon, of a nanowire of silicon. And we see that we have these local resonances where the optical mode is enhanced. So especially near these resonances, we can have a very strong dependence on the diameter. But it also depends on the amorphous shell thickness. which is something that is even harder to measure. Now the diameter, we could put it in an SEM or whatever tool to try to accurately measure it, but then to see how much is an amorphous shell, how much is truly our wire, is very hard to see. It also depends on the exact shape of the wire. So ideally you would need to do some cross-sectional imaging of your wire. It also depends on the distance to the substrate. So there are all these parameters which are very hard to determine experimentally, which can change your absorbed power easily by a factor of 5. And as such, also the thermal conductivity that you extract through these methods by a factor of 5, simply because you're either overestimating or underestimating your heat flow by a lot. Another thing that is for Raman thermometry is that since you are using the laser as a heater and as a thermometer at the same time, the maximum temperature will always be exactly where you're measuring. No, so your heat flow is always flowing away from where you're measuring your temperature, which is again a disadvantage when you're looking at inhomogeneous or especially at rectifying samples. But there is a workaround for this, which is being used here at ICN2 actually, which is to use 2 lasers. No, so you use one laser as your heater and you use another laser as your thermometer. And this way you can decouple the two, and you can measure your temperature even away from your maximum temperature point. You can control which direction your heat is flowing. So you can use it then to measure inhomogeneous samples, and it has been used for that purpose as well. Another thing for Raman thermometry, when we compare it to the electronic measurements, is that if you look at these kind of gradients that are going on here, we have a 400-degree gradient simply because Raman thermometry doesn't have as good a thermal resolution as the electronic measurements do. So you need a bigger gradient to get a nice signal to noise ratio, but that also means that you might get into nonlinear effects from the temperature dependence of your thermal conductivity. One way that you can overcome the problem of the contact resistance, of course, you can model it with this more advanced model, but as pointed out before, since the effect is comparable, there are series resistance, it can be difficult to extract the 2 parameters independently. However, if we slightly change our geometry and we only use 1 contact rather than 2, and we move our probe, then we see that instead of a quadratic profile, now our thermal resistance is increasing linearly with the distance from our 1 contact, and the 1 contact is only causing an offset in this measurement. So that means that the contact resistance and the wire resistance can be treated independently, because the offset of your linear profile will give you your contact resistance, whereas the slope will give you your wire resistance. However, this also comes with its disadvantages. Another workaround that we developed recently is to actually measure the absorbed power inside the system rather than relying on simulations. But like I said, to measure it with a simple power meter can be difficult for these kind of nanostructures. So instead, we relied on the suspended structures that you've seen before. As I said, these suspended structures are very good at measuring even very small increases in temperature. And since the increase in temperature is directly proportional to the heat that is flowing through these structures, we can measure how much heat is absorbed inside the wire, because the only way this heat can flow out of this wire is through this suspended structure and then through the beam. So by doing a separate calibration of how the temperature of this system depends on the power, we can use this to very accurately measure the absorbed power in any kind of system, really. And in that way, we can make sure that the absorbed power is truly corresponding not only to the specific wire or the specific nanosystem that we are measuring, but even to the specific geometry and the specific experimental setup that we are using. Yeah, so then again, I want to point out the advantages and disadvantages of Raman thermometry. What we saw before was that there were quite stringent restrictions on the sample node. Either they had to be conductive for the self-heating, or they had to be luminescent for photoluminescence. Here they have to be Raman active, which is from those three restrictions, I would say the least restrictive. Another advantage is that now we get the spatial information, although with a limited spatial resolution, and we also get much easier processing than we saw for the thermal bridge method. However, we are still in facing problems with determining the absorbed power, either through simulations or experimentally. The thermal accuracy is much lower than for electronic measurements, so you need bigger gradients to accurately measure the temperature. And if you want to have this heat flow control, you need to get two lasers, which also means that you need a certain sample size to be able to employ this kind of system. So the typical usage is for samples with a relatively high thermal conductance, because here we are not facing the same kind of problems from the very small accuracy of the Raman, and also for inhomogeneous samples, because now with the spatial information we can truly see what is happening in each different part of the wire. One thing that we did as well was to combine the thermal bridge method for creating the heat flow with the Raman thermometry for locally measuring the temperature. So the idea is exactly the same. Now we just put one platform at an elevated temperature and the other platform at a lower temperature. And with our objective, we are scanning along the wire to locally measure what is the true temperature of the wire. So we get rid of the assumption that we had in the suspended bridge, where we had to assume the temperature to be equal to the suspended platforms, but instead we are truly measuring the temperature of the wire, again by the peak shift. And then what you might see is something like this. No? So you will do a differential measurement where you measure the Raman peak when you apply the gradient versus when you don't apply the gradient as a function of position. And as such, you get, for each position, you get the effect of applying the gradient to the local temperature. So we actually used this system to do a measurement on what we thought was a quasi-ballistic system, or possibly hydrodynamic. I'm not going into that discussion right now. So what we did is, like I described before, we applied a gradient of 30 degrees. And what we found was that for wires that were diffusive with a larger diameter, we saw a nice linear gradient. Again, you can see the difference in resolution from the Raman thermometry and the micro bridge, where with the suspended bridges 30 degrees is already a relatively large gradient to apply to get a good signal to noise ratio. For Raman, you can see the error bars yourself. But the interesting part, I think, was that for the thinner wires, we measured that there was no temperature drop at all along the wire, which was a further confirmation that we were dealing with lossless heat transport within this system. So that is a unique measurement that we wouldn't have been able to do with any of the existing techniques yet. Okay, so now I made a really big table to just reiterate again the comparison between all of these steady state measurements. We have the two electrical measurements now, the Triomeca and the suspended bridge, and the Raman thermometry. If we look at sample requirements, then the suspended bridge has the least stringent sample requirements. And if we look also at the temperature range, then the electronic systems definitely have the larger temperature range that this can be applied, simply because at lower temperatures, the Raman mode doesn't depend that much on temperature anymore. However, with the suspended bridge, you suffer from very difficult processing, which you don't have with the Triomeca or the Raman thermometry. With the other two methods, we have the possibility at least to do local measurements. Of course, now with the addition of Raman thermometry to the suspended bridge, we now have that possibility also with the suspended bridge method. Yeah. So again, the typical samples that you would be measuring with the Triomeca are metallic stripes. Whereas for choosing between the suspended bridge and the Raman thermometry, I would recommend mainly looking at the conduction and whether you have the need to fully control the heat flow. Although again, that is possible also with Raman with the 2 laser. But if you have very poorly conductive samples, probably the high resolution, the high thermal resolution of your thermal bridge will give you more advantages. So you would go for something like that. And the thermal contact resistance, which is the biggest challenge for this, will not be that much of a problem. Whereas if you Raman thermometry, I would recommend to use for samples with a higher thermal conductivity, because then you're not limited by your resolution as much. Okay, so now I want to go to a very different class of techniques, but one that we've heard coming by, especially yesterday quite a lot, but also today we heard something about it, which are the pump probe techniques. Now, so now we see that we are looking at probably the most complicated setups. Now we see the lock-in amplifier that was all we needed for the electronic measurements. And we see the lasers and the objectives and the detectors. That was what we needed for the optical measurements, all combined into one big setup. And the idea behind this is that a pump probe will excite the sample and will change the temperature, and as such will change also the temperature properties. Now, so the typical properties that are measured with these pump probe techniques are either the reflectivity, when you look at time domain thermal reflectance, or frequency domain thermal reflectance, or the diffractions when you look at transient grating. But of course, we also already seen in the previous talk the photoacoustic measurements coming by. The reason, maybe in light of a question that was coming by yesterday, the reason why it's nice to have a transducer, or why often people will put a metal strip on top of these samples to do these kind of measurements, is twofold. But one of those reasons is, well, that was working better on my own laptop. But one of those reasons is, of course, our change of reflectivity is influenced by our change of temperature, but it's also changed by our change of carriers. No, so ideally you want a system where you are only measuring the temperature. You don't want to measure the change of carriers. So putting a conductive or having a conductive strip on top, or having a highly conductive sample, helps to get rid of this carrier effect, and thus makes you more sensitive to the temperature effect. The second reason that you might want to apply a metallic strip is that the penetration depth in metal is generally very small compared to semiconductor systems, and that allows for an easier modeling, where essentially you can assume a more 1D-like or 2D-like transport system. Okay, so also to quickly comment on the difference between time domain thermal reflectance and frequency domain thermal reflectance. So what we're measuring is the same. We are measuring the change of reflectivity due to a pump beam coming in. But what we're effectively measuring is still a little bit different. In time domain thermal reflectance, what we will do is we will modulate the amplitude of this beam in time. And then we will use a mechanical delay to delay the probe beam with respect to the pump beam, and to see how the magnitude of this reflectivity changes when you change the delay time. Whereas with frequency domain thermal reflectance, instead we look at the phase shift between the two beams, which is also influenced by the reflectivity. But then what you will see for a typical time domain thermal reflectance measurement is you will see a plot like this, which is the magnitude of your reflectivity versus time. Whereas for a frequency domain thermal reflectance, you will see the phase shift as a function of frequency. And then you can use certain types of models to extract what the temperature evolution was of the system, and what the thermal properties, so the thermal conductivity and the specific heats were of the system. The other pump probe technique that I want to talk about is transient grating. The transient grating technique can also be done in two ways, but the idea is now that we are measuring diffraction rather than reflectivity. So our probe beam is generally coming in at a different angle to measure the diffraction. And now we create a super lattice of conductive lines, and these conductive lines can be created in two ways. They can either be optically excited. You can optically excite a lot of carriers in your system and create conductive and warmed up lines like that, or you can already define metal lines on top of your system to create this. And then these the excitement exciting these lines will create a pressure wave into your system, which will change the relative distance between these lines even more, and that will change the diffraction. So a typical transient grating measurement will look something like this. I think the nice thing of the transient grating method is where with the time domain thermal reflectance and the frequency domain thermal reflectance, you will change the frequency to change the penetration depth, and thus the length scale, the typical length scale over which your transport is taking place. With transient grating, you can change the distance between these lines, and in such a way change the length scale over which your transport is typically taking place. But when you look at a typical measurement system, I think this was already coming by yesterday as well, you will see that again, you measure with a delay time now, so there will be a mechanical delay stage. And then you look at the diffraction signal. But the interesting part is that you can see two effects on top of each other. Yeah. Sorry, I will go fast. Two effects on top of each other, which will give you both the mechanical parameters as the thermal parameters. Okay, I will skip this in view of time. Can I real quickly? I want to talk real quick about the new measurements that we developed as well, which I think is relevant in light of some other presentations. So what we did here, again, we cantilevered a wire from a stripe, a suspended stripe, but now we did it in air rather than in vacuum, and the stripe was used as a Joule heater. So again, we see this combination of using the electronic heating and that we used the laser thermometry to locally measure the temperature. And now instead of using a heat sink on the other side, we use the air as a heat sink. Okay, so there's a model that you can use for that. But the problem with that model is that it depends on the ratio between the air cooling to transport through the wire. So you need to know one to extract the other. But since in this geometry we know how to extract the thermal conductivity using just heating with a laser, we can extract the thermal conductivity like that and use it to measure the transport through air. So what you can do then is try to model that with different equations. So in a diffusive case, you're effectively saying we are limited by the diffusion of our air molecules to take the heat away. And the other limit is the ballistic limit, where you're limited by the amount of air molecules available to take the air away, right? So here, what you see is a diffusion parameter, whereas here it's proportional to the pressure, so the amount of air particles available. And when we look at the typical geometries that we're using here, we find that we are actually ballistic over distances up to 700 nanometer in air, even though the mean free path in air is only about 70 nanometers. And the reason for that is basically that because of this nanoscale system, because of this geometry, we are always limited by the number of air particles that are impinging on our surface, rather than the diffusion limit, the diffusion of these air molecules. If I look at this number, I remember more or less the number that was mentioned in the talk this morning. I think we are on a similar order of magnitude for that kind of cooling through air that I've heard this morning. So I think this system can be interesting to study that further. But another advantage that we found, I will not go for the modeling, I think, because now I'm really getting late. But another advantage that we found is that when we have a finite mean free path, of course, so far I've always been assuming a diffusive transport model, but with a finite mean free path, of course, the system will change a little bit. So what we see here is that the solid lines are taking into account this quasi-ballistic effect, whereas the dashed line are assuming a diffusive model. So what we see is closer to the contacts, the quasi-ballistic causes the temperature to be lower than what you would expect from diffusive, whereas at larger lengths, it's actually going above the diffusive model. And that's exactly what we saw in our experiments as well. And the nice thing here is that when you compare it to a contact resistance, I'm not going into details in view of time, but the effect of contact resistance is exactly the opposite. No matter where you put this contact resistance, it will always cause the true signal, the true modeled signal first to go above the no contact diffusive model and only then go below. And if we compared it with other methods, before I showed you this ballistic transport method with combining the thermal bridge and the Raman thermometry, but you would get exactly the same result if you just had a very large contact resistance. And that is, true from model, from theory, and that's true from experiments. Now, if our contact resistance is much larger than a wire resistance, we get exactly the same result. So this offers a unique opportunity to extract these quasi-ballistic effects without having to argue that they're not coming from contact resistances. So then I come to my conclusion. I hope it's still in time. Measuring the thermal conductivity requires to measure both the heat flow and the temperatures. So because of this dual requirements, we have several techniques and several combinations of techniques that are currently being used for that. Decoupling the heater and the thermometer definitely gives more flexibility in that, but you do have to be careful that your thermometer doesn't start to influence your system too much. Then I would like to thank several people in the end. I want to thank the nanophononics group. These are several people of them where I used some data from, so that's why they're here. But I want to thank everybody in the nanophononics group for all the fruitful discussions that benefited to the understanding, and the same goes to Ricardo and Xavi from ICMAB for also the very fruitful discussions. And again, for organizing or co-organizing this workshop. And if I talk about fruitful discussions and being back into a workshop like this, a physical workshop, I also want to thank you for all the nice discussions we've been having and for listening to my talk. That's it.